Tony, that is bullshit.
I think it's C.
I think I'll take a different one. If one of us is gonna do it.
All right.
C.
Let's get going. Who says A? B. C.
Yes, sir.
1, 2, 3, 4. 4 votes for C. D. Some people who's not sure.
What's E?
Fair enough. Some of those C's were not sure as well. All right. So, how did you think through this one? Because this was an AP question, by the way. How would you think through this? Give me some ideas here. Then we'll get into the homework from last night. Then we'll finish up the lesson from yesterday. Hopefully, it's not as much of a disaster. That was painful. All right. Start us off. What are you thinking? Come on. Just looks right. No one. All right, let me guide you through this, but I'm still not bailing you out. What do you think of when you see 5 over n? Change an x over. Well, back up. Didn't our whole equation yesterday have a summation from 1 to infinity of something? Now, our indices were different. We had like I forget if they used an M sub k or a C sub k or what it was yesterday, but the index was different. But even though it's different, the format's still the same. And didn't it have a delta x at the end? Delta x sub k or delta whatever it was. What's delta x? The width of every rectangle is what? Smallest possible change in x. And how do you find out what delta x is? What was the formula we were going to use? B minus A over n. Well, that kind of looks like that, doesn't it? B minus A in this problem must be 5. B minus A is 5. If you have 5 over n, B minus A must be 5. Well, I look to the bounds. 1 to 6. That's 5. B minus A. Okay. Well, that doesn't really help me. All of those are B minus A of 5. But that's at least something to look at, right? Well, then I start thinking, isn't 10k over n, isn't that 2 5 over n's times k? Yes or no? 2 5 over n's times k? Isn't this 5 over n times k? Now, this is where I will not bail you out. I need you guys to understand this. Let's see if you pick this up. What is k? What's k representing in this problem? And in the problems we learned yesterday? We always like I had a k equals 1 to something. What is k? Anna.
Isn't it like the number of rectangles like within what you're measuring?
Yeah, so it's the number of rectangle you're on, right? Thank you. First, k equals 1, first rectangle. K equals 2, second rectangle. You with me? So, what's a 5 over n times k? Well, 5 over n times 1. Then 5 over n times 2. If k is 2. 5 over n times 3. If k tells you what rectangle you're on, isn't 5 over n times k how many 5 over n's you've gone? How many widths you've gone? Well, wait a minute. I thought k was going to infinity, right? N was going to infinity. K was 1 to infinity. What did those 5 over n times 5 over n's times k turn into if there's infinitely many rectangles? Turn into x's, don't they? Right? Can you see it now? Which one are we thinking now? Let's vote. C? D. All right, do you see D? It's D. We've got the two x's here. We got 1 plus x inside the square root. I think we can agree on that, right? Do you see how they are asking you to apply the idea of an index and widths and all that kind of stuff to convert? All right. We'll get into another one of these in a little bit, but let's go over the homework from last night. It was 1 through 9 odd. Now, the ones you saw in the homework up until 7 were what I call the easy way to convert. All right. It's C sub k's, and they have a delta x at the end. C sub k's turn into x's, delta x's turn into dx's. That's the easier of the two situations they're going to see. All right. Did you check your answers as you went? Kind of figure it out. Any questions in general about 1 through 5 odd? 1 through 5 odd, pretty easy. How about 7 and 9? The tough thing was it's not multiple choice. You had to write it.
Yeah,
Justin?
I was struggling to find the intervals.
Okay. Should we take a look at this?
7 and 9.
7? Let's take a look at 7 then. And hopefully that warm-up problem kind of helps us get things straightened out. Now, this is not a multiple choice problem, so we're going to have to actually convert directions. So rewrite the limit as a definite integral. So we're going to have, oops, that's terrible. We're going to be writing this symbol a lot. What goes on the bottom of the symbol? A, good, the beginning of the interval. And at the top, we have B, right, the end of the interval. So Justin's got a good question here. How do we know, you said what, how do we know what the interval is? That was kind of your main question, right? Let's talk about it. What do you think? What's that representing? Your delta x, right? So b minus a must have been pi. So what's one possibility? Pi minus 0. So maybe we go from, was it 0 to pi or pi to 0? What goes on the bottom again? 0 to pi. Okay, 0 to pi. Pi over n is your width, right? What's pi over n times k? Your width times how many rectangles you've done, right? So they're turning into what there? Pi over n times k's are x's, correct? So we have sine of x, and then delta x turns into dx's if the rectangles are an infinite quantity of them. Does that make sense, Justin?
Yeah. I was confused on like how it turned into x, but I got it now.
Yeah. So 9, number 9, our b minus a is 1. Now 9's bounds were 0 to 3. Any ideas why that's switched? It's not just 0 to 1.
If we're saying it's just a single value over n, are we just always going to say a is 0?
No. So that's kind of what we're kind of getting to with number 9. 9's a little trickier. 9 was the limit as x goes to infinity. Oh, sorry, n goes to infinity. Okay, equals 1. squared times 1 over n. All right. Correct answer? Number 9. It was 1/3 times the integral from 0 to 3 of the square root of 1 plus x squared dx. Or, okay, there's another possibility here. The integral from 0 to 1 of the square root of 1 plus 9x squared dx. All right, take a minute, talk to your neighbors around you to see if you can figure those out. Sometimes one of the best little like training wheels to get from here to here, like to get proficient in things, is to take a look at the answers and figure out, hey, how do they come up with that? Once you can start to pick that apart, then you're able to start doing it yourself. So take a minute, talk to each other, see if you can justify either one of those. Even better, justify both.
Let's go to the 1/3. So you know it's 0 to 1 because b minus a equals 1. I know it's 1 plus 3 times k to the n squared.
What's the 3?
Wait,
I'm confused. I was just turning the x, and I kind of got x squared, but it's like 9.
I think we should do this first.
I would convert it to
9k squared over n Or no, yeah. It's the same thing as 9 times k over n squared, or k squared n squared. Which is just x. K over n It's like I have a little bit of a concept.
All right, let's talk about it. I think the second one's easier to come up with. Would you agree? Like if you have your b minus a is 1, it makes sense 0 to 1 is your bounds. And then if 1 is your b minus a, then each k over n, like here we had 5 k over n's. Sorry, 5 over n times k. The 5 over n's times k turned into x's. Here it's going to be our 1 over n's. Here it's going to be our our 1 over n's times k are going to turn into our x's. Do you agree? Do you see a 1 over n times k here? So we have 3 x's. When you squared 3x, you get 9x squared under the square root. There's that second one. I think that one's the easier one to come up with. Who can come up with the first one? Right?
You can consider 3kn as like, you can consider 3 as the interval, and that means 1 over n is 1/3 of dx. And you can take that out of the interval, so it's the constant.
Good. Yep. Do you see that? Can you say it one more time?
You can consider 3 as the interval, because it's 3k over n.
So you're saying 0 to 3.
Yeah.
Okay.
And that means 1 over n becomes 1/3 of dx. You can take that out of the interval because it's a constant.
Yep. So that comes out there. And then what about in here? Your 3 over n is
That's the interval, yeah.
your x then, right?
Yeah.
Times k. All right. That one's for sure tougher to see. All right. Let's see. We left off yesterday. I think we covered any questions from the homework that you wanted to go over? Did you cover? Any questions on 1 through 5? All right. So we had this written down, right? I had to open up the old file, so yours might be just slightly different, or color scheme was different. One thing I want to mention, I didn't really get a chance to talk about it yesterday. When we talked about these variables matching, talk about those variables matching, it's similar to when we take derivatives. Like when I say take the derivative of whatever, you're going to want to know what variable you're taking the derivative with respect to. Because back when we did related rates, if I thought, we're doing a ladder problem and it's x squared plus y squared equals z squared, if I say find the derivative with respect to x, that's completely different than with respect to time, isn't it? So it's important to know what the integral is you're taking, what the variable is you're taking the integral with respect to. So these aren't always going to match up. So down the road, a little bit of foreshadowing, you're going to have to recognize how to adjust it if it's necessary. We're not going to get into that for a little while, but just a quick practice on using this notation. Let's do the easiest possible problem. What's the answer? No calculator. 15? 15? Okay, so this is just a practice in understanding notation. This is telling you, okay, this is like a translation problem. You know how sometimes in foreign language you have to I gotta translate this passage. Like this is math translation. All right, you gotta understand what's actually happening here. You have a graph, and if this notation tells us that f of x goes here, what's my f of x in this problem? 3. Well, what does f of x equals 3 look like? Horizontal line. F of x equals 3 is a horizontal line. And we're adding up areas from 0 to 5. Oh, that's just a rectangle. Base is 5, height's 3, area is 15. Okay? But again, the practice is understanding what the notation's asking you to do. What if I change this to an integral from 0 to 5 of 3x? All right, what'd you get?
50 thirds.
50 thirds?
Yeah.
Let's take a look. How'd you do that, Ryan?
That would be 25. I basically just took the antiderivative of the
We'll get to that in a minute. All right. What are we looking at here? We got f of x equals 3x. Everybody agree? So pretend nobody said the a word. Okay, antiderivative. If you have to, not that word. Don't worry. Pretend that you have to do this geometrically. Okay. Like the last one was a rectangle. What's this one going to be? Because it doesn't have its y-intercept is 0. It's just a triangle. 0 to 5. What's the height at 5? Well, isn't it 3 times 5? Isn't it 15? What's the base? Base of the triangle? 5. $15 times 5 is 75. 75 halves. What, 37 and a half? either way. Make sense? How to do it geometrically. All I'm asking you to do right now. You see an integral notation. This is called integral notation. It's how do I then find the area some other way, because I don't have a process for this yet. All right. So this we got into yesterday. Easy converting from sigma into integral notation. All the m sub k's. All the m sub k's turned into x's. That was easy. All right. Another thing you have to understand is how the integral becomes what's called an accumulator function. The AP test loves to test your understanding of this. I've already hit on it. If you find the area under a miles per hour graph, you're finding the miles accumulated, right? If you find the area under a barrels per hour graph, you're finding the number of barrels that have been accumulated. That's the idea. An area, the integral, is an accumulator function. It's going to have a ton of applications for us. Now, this notation is important. Do you notice? Write that down, but notice the variables you're writing down. All right, so a of x is our accumulator function, all right? We're calculating area from a, which is some constant, up to x, which is obviously a variable, okay? So this is called a variable upper bound, meaning I have a lower value that I know what it is. My upper bound can vary, all right? Now, the function that we're finding the area under could be anything as long as it's continuous. So here's the interesting thing. If I want to find out the area, what is the area function dependent upon? X, right? It's a of x. It depends on where you stop adding up area, okay? We're going to get a lot into this on Monday. I have a really good worksheet. It's going to look really old school, but I've used it for years. Every year the students say it helped connect the concepts, bridging differential calculus to integral calculus. It's a really important lesson on Monday, all right? And it's gonna revolve around this whole idea, okay? There's a big idea that's gonna connect first and second semester for us. All right, and you don't need to write this down. We've already defined the definite integral. It's called a definite integral. All right, now something you need to understand about area. And again, we are going through this process. We're not going to spend weeks on like we did on limits. This is just, here's the highlights. Let's get starting to use it next week. All right. So area, if you've ever been told area can't be negative, that's a partial truth. All right. Area can be signed. You can have a positive, you can sign area as positive or negative. All right. So if you want to get into semantics of it and say area can never be negative, okay. But let's sign this area as a negative value. Like let's give it, I don't want to say direction because you guys are, but it's similar to that concept of giving it some sort of value, but then also assigning it a positive or negative entity, for lack of a better word. So this is what the integral is going to do for us. Now we're going to learn a process next week on how to evaluate this by hand, not just geometry. Because if I say here's the find the area and it's a triangle, easy, half the base times the height. Rectangle, length times width. If it's curved, now we're in trouble, right? we're not going to be using rectangles long term. The rectangles were a stepping stone for us. The person who discovered this found out not how to approximate areas with rectangles, how to find the exact area under a continuous curve. So we're going to learn that process next week, but you have to understand when you do the process, it's going to find the area above the x-axis minus the area below the x-axis. We're going to call that a net area. Okay? So if you have a graph that looks like this, I don't know, let's pretend we know a graph that might look like that. Let's call it sine of x. I don't know. From 0 to, well, sine goes up to 1 at pi over 2, good. And then it hits the x-axis at pi, goes down, it reaches a minimum at 3 pi over 2, and then it comes back up and at 2 pi, right? So if we take this at its word, then the integral from 0 to 2 pi of sine of x dx should be what? 0. Positive area, negative area. What's the net area? 0. Take out your calculators and let's do that. My calculator is not quite ready yet. I think, right? Not quite. I need to put in the license key.
You might be able to use it for a trial.
I'll add the student software. Shouldn't matter. All right, your integral symbol, your definite integral symbol. Okay, we're actually not going to go to the graph right now. Not yet. We're going to go out in the calculator window. It's under the templates button, which is the button to the right of 9. And it's towards the bottom row, I think. Or is it the middle row? Is it the middle row now?
Middle right.
Yeah, middle far right. Just on MS. And you're going to have to fill in the boxes. So you're going to have to put a 0 for the lower bound, pi, or 2 pi for the upper bound. Make sure you're in radian mode. Sine of x. Yes.
Or you might tell you we just get it.
No, we did it just like this. You talked about it. I can't get up there.
We interpreted how to do it.
Where's why would you play so many buttons to get sound? Yes. Remember they can fix this. Remember they can move the areas. We paid. You're
I got 0.
Did you get 0? Now, what do you think the integral from 0 to pi would be? Any guesses?
wow.
Tony.
I know, bro.
You're wrong.
Yes, that's my guess.
Interesting.
This one would not be his fault.
The folder doesn't have the software for the Inspire in it, so I just took a guess on which one it was. That's the right answer. 84.
Well, maybe you should have put it in.
Why would I?
Did you get 2?
That's crazy.
No.
What'd you get?
Oh no, I thought you were talking about our guesses. I didn't guess it.
Isn't that weird? Let's be honest for a second, okay? And maybe you think you're too cool for this class, but let's be honest. Sine of x. No, it's okay. Say we have an arch of the sine curve. An arch of the sine curve. It's weird that the area is exactly 2, isn't it? I mean, there aren't very many nice numbers on the sine curve. Yeah, it goes up to a height of 1. Yeah, it goes down to a height of -1. But for the area to be exactly 2, that's kind of interesting, isn't it? All right, here's another way to do the same thing in case you're in a graphing window. If I'm in a graphing window and I graph sine of x.
Oh my goodness.
Nailed it.
That was impressive.
Thank
Julie,
you.
what was
I
that?
practiced.
It's work's turn.
All right, ready? Menu. Analyze graph. Integral.
No shot.
Now, I thought you were going to say something different. All right, lower bound, 0. Upper bound, pi. Enter. And the nice thing is it'll shade it and give it a value.
I got 0. I don't want to go to that. I have all my tables still open. How do I get rid of those?
Control T.
It's your first day with Calc.
You tell them, Pat.
First time I've been using the tables since day one.
All right, so there's just a couple little highlights for how to use the calculator to find intervals. Now, we're going to be doing it by hand a lot. But these are nice ways to check your answers if you are confused. So what is my point here? Okay, I need you guys to look up here. Listen, this is very important. It's going to come up every time. When we do this by hand, eventually, when we do this by hand, okay, we're going to get 0. We're going to get 0 by hand. You don't have to manually say, oh, wait a minute, that's a positive area. That's a negative area. I need to make that negative, make that. No, it's going to, the math behind it is going to take care of itself. Okay. So this is how you're going to have to do this. Now, there's another application we're going to get to later. It's called total distance traveled. Okay. And I need to introduce it because it's going to be a lot of times we're going to be talking about this. Here's the analogy. I'm going to use that velocity time graph all second semester. And that's the reason why we're doing the driving activity. Okay. Part of your homework this weekend is going to be to calculate RRAM 30 for the driving activity and LRAM 30 for the driving activity. All right, it's not going to take that long because guess what? Once you've done RRAM 30, one of the values you're going to take out and you're going to have to include a different one, right? For LRAM. So it's pretty easy. It's not going to take you long, but having that as an experience and a calculation that you can go back to, I want that to kind of guide us through the second semester. Here's what I'm talking about. How many of you have done, well, we've done velocity time graphs here in Calc, but how many of you did velocity time graphs in physics where you're talking about motion on the line, right? Okay, so if I'm moving to the, my only options are on a number line. If I'm moving to the right, my velocity is positive. If I stop, my velocity is, if I'm going this to the left, my velocity is negative. Okay, here's an example. I start at a position of 1. Position of 1. Okay, I go to the right. I stop at a position of 10. I come back to a position of 1. What's my displacement? 0. Here you go, ready? Let's pretend this is a velocity curve. Pretend this is a velocity curve. Say it's feet per second. What's the area under a feet per second graph going to give you? Feet. Ready? Velocity is positive. Reach maximum velocity. Velocity is getting closer to 0. What did I just do right here? Velocity is negative, getting more negative. Velocity is negative, getting close to 0. What was my displacement? 0. Okay. This is a displacement argument right here. Okay. The area under a velocity curve is your net area. It means displacement. Do my legs feel like I walked 0 feet? No. How do I calculate how many feet my legs feel like they walked? Is that absolute value? Good. What would the answer be for this example? How many feet does it feel like I walked? 4. 2. Not -2 anymore. That needs to be treated as a +2 because I feel like I walked 2 feet there. Okay, that's going to be called total distance traveled. We're going to have to manually do something different if we want that to be treated as a positive. This is just a little bit of an introduction of where we're going with this, all right? So the area under a curve is your net area. It's your displacement if it's an area under a velocity, all right? It's net area. So for a constant, you don't really need to worry about this. We've already done the constant. We did the example, I think it was 3, right, from 0 to 5. What'd you do? Base, 5. Height, 3. Done. All right. And then I just showed you how to do it in the calculator. So let's do this. Now, this is NINT. This is if you have to go back and use your 84. You don't want to do that. So in our Inspires, what you're going to do is in a graph or calculator window, we're going to go -1 to 2. Just to practice typing it in. -1 to 2. X times sine of x dx. What should the answer be? A number. A number. Our calculator tries to outsmart us. It's like, hey, I got a really, really technical way to write your answer. Okay, I don't want you to write decimals. That's just not accurate. Here's your answer. We're like, actually, I wanted a decimal. Okay, I really wanted to round to 3 decimal places. So here's what you do. Okay, don't panic. You need to write down a decimal. Hit Control Enter. It'll give you the approximate value. Control Enter gives you the approximate value. So 2.043 or 2.042. Some of us are still not rounding out to 3 decimals. Please, I'm going to have to keep counting points off. Okay, if you're not rounding out to 3 decimal places. The AP graders will for sure count points off. So here's how we do it in the calculator. They didn't even write it. Lazy. 2.043. All right. All right, let me double check the assignment for tonight. What do you think? I think this is 7th grade. Did you bring your popcorn money?
Wow, that was disrespectful.
What a throwback.
I wasn't trying to disrespect you.
That was
like
disrespectful.
The
popcorn money was heat.
Anthony, dude, that was when we took our memories. He's stealing your popcorn. Popcorn day went crazy.
That's like, it's okay, dude. Just said it was good.
Don't forget the multiplication symbol.
And you would only want the yellow pieces.
Hold on, don't write this down yet. Don't write this down yet.
Dude,
I knew that kid that brought in like $3. Bought like bags and take home. Oh, like it's so good. Dilly, write this one down.
Yeah, Dilly.
Tony, did we ever have a class together?
No. Ever.
There, Dilly.
Except for China school.
I didn't go to school.
We have to work with you.
All right, 21 and 24, the directions say to use the graph of the integrand. All right, what is the integrand? It's the function. Listen carefully. The bounds are the beginning and end of the interval. The integrand is the function that you're finding the area under, okay? So the directions for 21 and 24 say use the graph of the integrand and areas to evaluate the integral. So when they say and areas, they're implying, hey, maybe there's a geometric shape that's created here. I don't know, a trapezoid, a semicircle. Use the areas of the integrand. So you might need to graph the integrand. Now, you could cheat and you could plug it right in the calculator. Okay? Some of you will. You know who you are. Others will be like, no, that feels dirty and wrong. I won't do that. And you're going to try to use areas. And I'll see your area calculation. Okay? Next, I would like for you guys to calculate the LRAM 30 and RRAM 30 for your driving activities. Please keep in mind, you did 10-second intervals. What do we want our answers to be in? What should the area under your miles per hour graph be? Miles, not kilometers. Miles. But wait a minute. You have miles per hour, but you have seconds. Sounds like conversion time to me. Converting your 10-second intervals into hours. Hopefully it doesn't take you hours to do that. All right, so what am I trying to say? After you do those LRAM 30 and RRAM 30, your answer should be very close to how far you actually drove. I want you to compare that, okay? So from your odometer readings, subtract final minus initial to get how far you went. See how close your calculation is to that. Closest one gets a free high five, piece of candy. I don't know. I have a math award. Would you like a math award?
Yeah, we did the project at the end of the year, and I had this big bag. And like doing like a nude in Dakota. Oh yeah. So this is talking about yeah, that was crazy.
We did like the drama at the start.
Yeah.
That is huge.
I mean, that in third